Stability of equilibrium points, more specifically, stability in nonlinear systems. Stability analysis of nonlinear systems. Last time we saw a graphical analysis. Graphical analysis for stability of nonlinear systems. We said that can be done for only first order, for first order nonlinear systems, like plotting rate versus state, or at most you can perhaps plot rate of each state versus the two other states in three-dimensional flow. Then again you can do the in three dimensions this type of derivative analysis for stability. But that's the most you can do. Beyond that, you can do partial incomplete stability analysis by pairwise plotting of each rate of change of each state versus each state. Well, but that would be an incomplete information. But sometimes done to get some idea, do some guesswork, partial mathematical analysis of stability. A more complete analysis for stability of higher order nonlinear systems. So, I don't know I don't remember what you call it. Did you call it A or 1?
Oh,
First order. Huh? This is now 2, right? Is this correct? Higher order nonlinear model. Stability analysis for higher order nonlinear models is done by called linearization or sometimes called perturbation analysis. They are similar methods, they are very similar. I'll discuss more strictly the linearization approach. Perturbation approach is very similar to, it's a very similar method, just looks sometimes slightly technically different. Perturbation analysis. Now I will illustrate on a second order system, but as you see we can generalize it. I will illustrate on a second order nonlinear system. So the example, we demonstrate second order system. The second order system looks like this. V squared y over dt squared equals, here is the general form of a second order Here's the general form of second order nonlinear model, right? This is the most general form of a second order nonlinear model. Here, the highest derivative equal, can always be put in this form. As a function of, nonlinear function of y, dy, over dt, and t. Now, for stability analysis, without loss of generality, the non-homogeneous term does not affect stability in any subtle way. Either you have a stable input function, in which case it has no influence on stability. Okay? So if it's a stable input function, meaning what? E to the minus t or constant, right? Some sort of function, some function that in the long term does not diverge, okay? Converges. In which case, if you ignore it and you do the homogeneous stability analysis, you have complete information. Or if the time function is a unstable time function, diverging one, such as t squared or e to the positive t, right? Or even simple t, in which case, of course, the system will be what? Unstable. Again, the result is trivial. No matter how stable the rest of the system is, if you force it with a growing function, the system cannot settle at the equilibrium point. The equilibrium point cannot be stable. You see? With a forcing, increasing the forcing function over time, right? That's just obvious. Okay? So whether it's linear or nonlinear, stability analysis, the interesting part is always done, the non-trivial part is done on the homogeneous portion. So you always assume that this is just Fy dy over dt, assumed is used, or assumed or used. Homogeneous. Assumed homogeneous. Alright, so keep that in mind. Alright, so again, you don't lose any interesting information when you do that, because the rest of the non-homogeneous part is trivial. Alright. So what we will do then is, so we linearize f of y comma dy over dt is the real nonlinear function around y equilibrium, right? And what's the second component? We will linearize this, the linearization is a nonlinear function. We will linearize it around the equilibrium point. And the equilibrium point is what? Around each equilibrium point. And around each equilibrium point, which is y equilibrium, comma, dy equilibrium over dt, which is what? 0. So you will recall Taylor's expansion. This time it's in two variables. Well, in one variable, I'm not going to write in one variable. Okay, in one variable, we already know, we keep using f of x 0. Let's just say f of x equals what? F of x 0 plus, right? You know, the Taylor expansion of f of x is what? F of x 0 plus, huh? X over x 0 times the derivative and then plus. But the linearization only takes what? The first term. The first term is linear. So I'm not writing in the simple one variable Taylor expansion. More interesting one for our case is in two variables, it looks like this. Fxy is two variable, two dimensional Taylor expansion. Around some x0, y0, this is y. x0, y0 equals this plus x minus h0 times the partial, the derivative of what? Of f with respect to x, right? That's x0, y0 plus, then what? Y minus y0, second difference between the second variable, times derivative of f with respect to y, then plus x minus square over 2 factorial, right? Second derivative of f with respect to x plus I'm writing these, but I'm not going to use them, so I'll stop here. Well, I'll stop. Then you have the cross product and the derivative to one, then with respect to the other, dx, df, square of dx, and then dy, so forth, right? Yeah, this is the general. Now I will say it's the equilibrium point in the next slide. Yeah, this is the general around some point x0, y0. But now I will put equilibrium point. So I don't need all these terms. If you get rid of all these terms, then it's called what? Taylor series linearization, right? So you call this. This is linear, right? Because this is a number, this is a number, and these are just, you know, linear functions, you know, because it's numbers and x numbers times a number. So this is linearization. Linear. So linearize, we forget about that. Okay, applying to f, what's our function? F, y, dy over dt, around, as you say, the equilibrium point. An equilibrium point, because the linear system may have many equilibrium points, but around each equilibrium point we will do that. The equilibrium point is x, y, e, comma 0. Right? So it looks like this. F, y, dy over dt equals f of y equilibrium comma 0. Right? I'm just applying this to this case. Plus y minus y0 partial of x with respect to y. Is this correct? Y minus y, not y0, that's y, right? Huh? Now I call this y. Y minus ye times partial of f with respect to y, evaluated at y comma 0. Plus, what's the next one? Y. Huh? What, the next one is? Y minus 0. Y minus 0, which is y. So it's times what's the second variable? Huh? Second variable is dy over dt. So it's dy over dt minus 0. Right? So with y minus its value. Do you agree? Dy over dt minus, you said y minus 0 or dy over dt minus, maybe you said it that way, I don't know. Do you agree? So dy over dt minus 0. Is this correct then? Times what? The partial of f with respect to dy over dt. Right? The partial of f with respect to dy over dt. Change notation there. Evaluated at again what? Y equilibrium comma 0. So you stop there. But you ignore the rest. This should linearize. What's more interesting, you should note that what's the value of this? Huh? By definition, this is what? How do I find the equilibrium point? The equilibrium point is the point that makes this what? 0. So it's even simpler than this. This is 0 by definition. The equilibrium point is the point such that what? All derivatives vanish. So this is equal to the f is equal to 0. In addition, dy over dt is 0 too, but f is equal to 0 too. The function must be equal to 0. So now, note that the problem becomes even easier if you don't have dy over dt in it. Then it becomes in one variable. If you don't have dy over dt, then it becomes Taylor expansion in one variable. in y only, as you see the example. But if it's a dy over dt, then it's a two variable Taylor expansion. Let's see a simple example first.
dy over dt is 0.
Huh? dy over dt?
Is 0.
Yeah.
And so the second term very close also. And dy over dt minus 0.
No, dy over dt is 0 at equilibrium point. Yeah, at equilibrium it's 0. That's correct. So this is like y. That's just general variable dy over dt. dy over dt at ye is 0. Okay. So when you try to find ye, you say dy over dt at ye is equal to 0. Find ye is equal to 0. This is not only at the equilibrium point. This is the behavior of the function of the function linearized, approximated around the equilibrium. So let's see first an example in one variable only. So this is d squared y over dt squared equals 1 minus 0.1y times y. Here's an example. Okay. So what do we do? The general approach is what? The general approach is first how to find the equilibrium point. So to find the equilibrium point, you write what? 1 minus 0.1 ye times ye equals 0. Right? From here, what are the equilibrium points? Ye 1 equals 0 and ye 2 equals 10. So I have two equilibrium. Then the question is stability, right? So what do? I linearize around each equilibrium point. Linearize around each. This is the first equilibrium. First, around y equilibrium 0. But let me just do something here. To linearize around each equilibrium point, first let's define our function and let's take the derivative because I'm going to use them over and over again. So the first, before you do around ye, on top you say, in general my f of y is what? My f of y is what? 1 minus 0.1 y. And my partial of f with respect to y is the partial derivative of f with respect to y. So these are the functions I will need in my Taylor's expansion. In most cases I will need those derivatives. So this one is 1 minus 0.2y, right? Okay, so this is important for me, the general first step. Okay, note immediately that this is why I call the simple case. I don't need the other one, this one, because that doesn't exist. There is no dy over dt. So this is the first one we are doing in the simple case. So it's fairly simple. So I say f of y. This is now a single variable. This becomes now not this, but a single f of x around x0 type of Taylor's expression. F is approximately equal to linearize. F of what? F of x0, f of 0, right? Or f of y0, whatever you call it. F of y0. f of y e, which is 0, plus what? Y minus 0, let's see if you agree with this, times 1 minus 0.2y evaluated at y equals 0. Is this correct? Let's see if you agree with this. F of ye, right, plus y minus ye times derivative evaluated at ye, right? There is no other one. There is no continuation. There is no f of y e comma dy over dt. There is no dy over dt. Right? That's all. Single variable. So this one gives you y, right? The result is y. Why is it y? Why is it y? Why? Because this is what? What's this? By definition, just talked about it. By definition, this is 0, so all we have left is what? Y. Alright? So, now you see what we mean by linearization. What happens is, the linearized, so, around ye, d squared y over dt squared, remember this, is approximately equal to what? Y around, in the close neighborhood of what? In the close neighborhood of 0. Then you have a function that goes like this. Okay? And then you say around the equilibrium point, the curvature can be linearized, reasonably linearized by this function, and this is enough for me to tell what? Remember this analysis, whether to go to the left or to the right, that derivative analysis. Positive on the left, negative on the right, this is enough. So you do that. So and how you do it? Yeah, you can just solve this around y you do. And I don't know how you want to do it. The tradition, standard approach is what? Take a look at the eigenvalues, right? So the eigenvalues is a linear model. R squared equals 1. The eigenvalues. R equals plus or minus 1. What's your result? You say in this nonlinear model, the equilibrium point 0 is what? Huh? Why? Because of a positive eigenvalue. What's the next one? 2 around y equilibrium 10. This guy looks like this. F of y approximately equals to f of 10 plus y minus 10 times 1 minus 0.2y evaluated at y equals 10. This is equal to what? Huh? What's this guy? This guy is 0 by definition. Y minus 10 times minus 1. I will leave it like this. So there is a little trick that you often use here. There are two ways of doing it. You just pick and choose your. So it is then thus so the linearized function is d squared y over dt squared is approximately equals to y minus 10 times minus 1. Why am I writing like this? Now either you multiply it out and what do you get? You get minus y plus 10 and then you ignore completely 10. Remember? Because 10 has no effect in stability. And you do the stability analysis, so d squared y over d squared equals y equals minus y. Do you agree? That's one way of doing it. There is a more general, sort of neater way of doing it. You reach the same result. That's why I kept. You call this the displacement from the equilibrium point. Because if the displacement grows, then you have unstable. If the displacement shrinks, then you have what? Stable. So the equilibrium of displacement is 100% equivalent to the not equivalent. Stability of displacement is equivalent to what? To the stability of the variable itself. So what? Sometimes here is a way.
Plus or minus
Ha?
equilibrium'dan plus or minus koyabiliyoruz. Sonuçta 10 ile
Z equals let Z equals y minus 10 sort of displacement from the equilibrium. From y in. Then dz over dt will be what? Dy over dt, and d squared z over dt squared will be derivatives. All derivatives are the same. Do you see them? So then d squared z over dt squared will be what? D squared y over dt. So what do I mean then? Then you go over here and here's what you have. Then d squared z over dt squared equals minus z. Is this correct? Is this correct? This is minus z. This is z. This is minus z. And this is nothing but what? You can call that d squared. So you have an equation that looks like. The other one was the same. Do you remember the other one? D squared y over dt squared is equal to minus y. By ignoring, you get the same thing, but this is just sort of, it's just a convenience that people use and can sort of generalize this for the displacement analysis in terms of stability. So you are shifting the first equilibrium to zero and then analyze. That's what you do. But in any case, what do you do? So this is linear, right? You write what? Eigenvalues. You have r square. This time is equal to minus 1. Huh? Right? Which means r equals plus or minus pure imaginary, yeah? Plus or minus just let I. Huh? Imaginary. So what's your conclusion? Real part is what? Zero. So borderline scale. Because real part is zero. Real of R equals to zero. Now, borderline stable means that it's not asymptotically stable. It's not asymptotically approaching it, but it's nevertheless stable. That's borderline stable. Make a little note here. The borderline stable result, you can guess. It's not hard to guess this. It's not 100% reliable. Why? Because you linearized it already and you obtained borderline stable. Now you are suspicious. Why? Because if it's so borderline stable, and if my linearization creates an epsilon error, I may get that perhaps in a slightly modified, slightly disturbed version of the model, I may get a small positive real root here. So in general, the borderline stable result, as a result of a linearization of a nonlinear system, gives you a what? A weak result. So I'll show you some examples of that. It gives you a weak result. And then you should do further analysis. When you get this, usually you do further analysis, but that's the advanced version. Sometimes, in many cases, it's valid. In many cases, it is indeed borderline stable. which means we have constant oscillations around. But let's see. Let us see before we see more complicated examples, let me show you. We have to do one thing, right? We can also apply this to a first order system. There is no requirement here that says what? This is only applicable to a second order or third order system. By the way, if you have a third order system, then it would be a Taylor expansion in three variables. You see that? Because we have third derivative, y, d squared y over dt squared dy over d, in which case you would have a Taylor expansion in what? Three terms, three variables. Do you agree? So keep that in mind. In general, nth order will have what? In n terms. But what about first order? So the question is, first order. Can we apply? The answer is yes. So far we saw first order by what? Graphical analysis. And which first order system do you think we'll analyze? Huh? What? Yeah. So we say, I mean, by the time we are finished with these two courses, you become the top expert in the world on density-dependent growth model. But you are lucky because I can prove to you that if this is the only model you know in the rest of your life, you can still be a person that you can get some job. Because this is used in marketing, this is used, I'm serious, this is used in epidemiology, very serious use in epidemic dynamics. Of course, richer versions of it, but the basis is that it's used in population growth, demographic studies, in epidemiology, in marketing, at least. You know. But there are other uses as well. So this is quite famous. But anyway, so we had something. The version we used was like this. Huh? This is the version we used. So we are not going to do the equilibrium points again. What are the equilibrium points? Yeah. Those are the equilibrium points. And the function is this, right? This is f. Okay. So you see, now, obviously you have as one term, one variable Taylor function, expansion, because all you have is what? F of what? P. We are going to linearize f of P. That's all we are going to do. Don't have anything else. This is much simpler. What I'm saying is there is no situation where you may have it dp over dt, dp over dt is already on the left hand side. So this not p. The derivative of f with respect to p is equal to lambda minus 2 like this. Yeah. Yeah, like this. So around Q over dt is approximately equal to that f of 0 plus p minus 0 times do you get just this? This is what? What's the first term? F of 0 is 0 by definition. So you get P times gamma. And how do you analyze? Now this will take, this is a lot of work, right? What's the stability of this model now? This is good. Yeah, you know this. You look at it and you already know the solution. You can do it in 3-5 different ways. You can just look at this positivity, positive feedback to non-stable. The root of this is what? R equals what? Gamma. You can do it like that, or you can just write down the solution. Right? P of t equals e to the. So since gamma is positive, we assume that gamma is positive. Gamma is positive. Right? So unstable. This is positive, unstable. We already knew this result, right? You knew it from 3 or 4 different ways. And then what's the other one? Around equals? Yes. How does that work? So then around PS is P over T is approximately equal to F of PS plus P minus PS times P over PS evaluated at PS. This, so did you already do it? This is 0. P minus PS times what? What's this guy? Huh? P minus PS times, that is just, yeah, minus gamma. Can you again do this discrepancy or displacement analysis? We can call this Z, right? In which case, what do we get? dz over dt will be equal to, is this correct? This is displacement model, right? dz over dt equals minus gamma d. So what do you conclude then? The root is negative, therefore PS is stable, asymptotically stable. Alright, so finally we can see a little bit more interesting example. The more interesting example then involves a full-fledged second-order nonlinear differential equation. So this one looks like this. d squared x over dt squared plus 2 dx over dt plus h cubed equals 0. I made this up. This is a nonlinear model. It has full terms, all the terms, d squared x over dx over dt. Alright, so what is f in this equation? F in that terminal, in that term jargon, our f is what? F of x, comma, dx over dt. Huh? Right? Is equal to what? Minus 2 dx over dt minus h. Now, yeah, or if you want to write in that order, you can say minus x. That doesn't matter. Minus h cubed. This is our function. And what are the equilibrium points? How many equilibrium points does it have? Huh? Do you know the equilibrium point, huh? Yeah, but they are all 0. So, you know, if you do analyze, you analyze 3 times 0. So they are right. So the only equilibrium point is then what? X equilibrium is equal to what? It is equal to 0, and of course dx over dt at equilibrium 0. X dot equals 0. That's all. Okay? So the equilibrium point is 0, and X dot equilibrium equals 0. Alright? So now we will analyze the stability around this point. Alright? Now, well, the derivative is of this function I will need in here. I will use this Taylor expansion. So what do I need? I need first of all df over partial of f with respect to a, right? And what's that? Minus x squared. But I also need this uglier one with respect to. Do you agree? This is minus. This is minus 2. Yeah. So I have my 2 derivatives. Then I can linearize around the equilibrium point, which is what? Xe comma 0. And the second 0 is what? I'm sorry, Xe equals 0 comma 0. The first Xe is 0, the second 0 is what? X dot equals 0. So it becomes 0, 0 in a nutshell. So it looks like this. F of x dx over dt, my function, this function, then should be approximately equal to f at 0 comma 0. Do you agree? Plus what? X minus 0, is this correct? Times what? Times what evaluated as what? This minus 3x squared evaluated as 0 comma 0. Alright? Plus what's the other one? Dx over dt minus its value, which is 0, evaluated at, and what the function minus 2 evaluated, that doesn't matter. So this long story becomes what? The first one is what? 0, first term. Second term is also 0. Huh? It's also 0. So I have just what? Very simple. So this is approximately equal to what? Minus 2 dx over dt. So that, therefore, when I linearize my function, my nonlinear function, my differential equation becomes this. D squared x over dt squared is approximately equal to minus 2 dx over dt. Do you agree? Instead of being equal to what? Minus 2 dx over dt minus x cubed, you are saying when linearized, it becomes approximately equal to simply what? Minus 2 dx over dt. That's what it says. Just get to go. I just said it could be easy. Let's just throw it away. Alright? So let's see what result we get then. So this is linear, so you can analyze this linear model. This linear model, then what kind of eigenvalue equation does it have? R squared plus 2r equals 0. Huh? So r equals 0 and r equals minus 2. That's your conclusion. So the point 0, 0 is then what? So 0, 0, this equilibrium point is stable.
It's a borderline stable through repeating.
No, no. If you had, you don't have repeating 0 here. If you have repeating 0, it would be unstable. This is not the borderline stable. We use that term when you have pure imaginary roots. This is stable. Okay. This is pendulum. You know the pendulum model? Yeah, pendulum model is sometimes discussed in physics in different ways, different versions of pendulum model. One of them is the simple nonlinear model. Yeah. This is the one, right? Yeah. Yeah, this motion is not quite linear when you take a look at the model. This has damping, of course. We write down, I think, a model without damping. It looks like this. We are not going to discuss, of course, pendulum model. That's not the purpose of this course. But it's neat that we have an example, right? It is a pendulum model. Just like this. This angle is your variable. You know, you measure the movement by this angle, theta. So it's just like this. This is the vertical, and this is the pendulum. This is the angle theta. And the movement you measure by theta. So it looks like this. When you write down Newton's law for theta, it becomes like this. G is the gravitational force, and you are sort of projecting the gravitational force by using sine theta into the direction of the motion. So this is one simple, well-known pendulum model. We are not interested in building the model or discussing all details of the model, but the question is the equilibrium points and stability. Now, what are the equilibrium points? The equilibrium points are minus G at the equilibrium point. Of course, going back to this is your F, right? And the derivative will be 0. So G sine theta equilibrium equals 0, right? So what are they then? Theta equilibrium equals what? Sine, when theta is 0, sine is 0. Right? So one obvious one is what? 0. But is there another one? Yeah, and all the multiples. We are not interested in all the multiples, but to cover the whole range, the only other possibility is what? It is pi. If theta is pi, it's still, I mean, if this is not like this, if this is a rigid bar rod, then if you turn it upside all the way up, then physically you know that it's an equilibrium too. It can stay like that if this is rigid, right? You cannot do it. It's very hard, but in theory, all the forces will equal when it's down here, or when it's a pure vertical position, whether this way or this way. It will be stable. But physically, you know it, but mathematically you find it too. You have two equilibrium points. Okay? So, let's assume that this is a rigid bar so that it's possible. Okay? So that physically speaking and mathematically speaking, one equilibrium point is here, the other equilibrium point is up here. Alright, when it's all the way up. Alright, so we have two equilibrium points. Now my F is this is my F, and I will use this methodology. So Derivative of f with respect to what? Theta. I am using, that problem is sort of like this. Why? Because I don't have dy over dt. You see, I don't have d theta over dt. It's sort of a simple problem. It's not as complete as this one. There is no d theta over dt in that problem. And why do you think there is no d theta over dt? Because I ignored that what's missing there, physically speaking. D theta over dt comes from friction, or whatever you call it, damping, friction, resistance. Something that resists what? Gradually stops the motion. You remember the spring model? The theta over dt term comes in general from, in these physical models, they come from what? Some sort of friction that resists the motion, right? So here I am assuming that right at time, we are assuming that a vacuum. No friction, no air resistance, nothing, right? So it will move, you can guess, forever. Okay? So anyway, so for that reason, there is no the theta over dt, and so this becomes, what's the derivative of sine, right? Cosine. So it's minus g cosine theta. That's the only point. All right. This is it. This became a very high-tech lecture environment because, you know, anytime I need an exam, I finish the lecture and then I show you and then I put right and I show you again. This is neat, right? That's what your wife should use. Okay? Your wife.
Pendulum.
Huh?
Yes.
Yeah, when you pendulum model, and then she should have something like this. So she uses a method. Way of having a virtual laboratory and a physical laboratory in the same class. All right. So around linearize first around what? 0. What do you get? You get this. And d squared theta over dt squared equals minus g. No. Am I writing it down? So this will be equal to f of first f of what? F of 0, which is 0. Then what? Minus theta minus 0 g cosine 0. This minus just comes from here. Yeah, this plus. I just put it there because it looked ugly the other way. Yeah, you know, like, I was just about to write plus and now I changed it to minus. There is the plus negative is here. Okay. So what was cosine 0? Cosine 0 is 1, right? So what's the result then? Huh? Is it minus g theta? G is a positive number. So what do you write here? L, I am assuming that L, G are positive, right? So what do you get then? So what do you get from here? Yeah, you're right. They are both positive. Put that on the other side, you get another positive number there. So what do you get? Is it exactly like this one? Or is it this one? This one. Huh? So then you just say R1 to pure what? Is it pure imaginary? Yeah, you can extend. Just plus or minus I G over there, right? Pure imaginary. Actually, you can write down if you want plus or minus G over there. square root of G over L, right? No, G over L. Ah. Okay. Okay? So what's your conclusion then? Borderline. Şu mu aynısı? Ha? Şu muydu? Yok yok. Bununla aynısıyla alakası yok onun. O tamamen imaginary çıkıldığı için. Second derivative bu. Anladın mı? Second derivative ya bu. Dolayısıyla r kare eşittir eksi bir pozitif sayı çıkıyor. Şu an eksi bir pozitif sayı diyorum. Eksi bir sayı çıkıyor. Çok güzel bir şey.
Eksi pozitif sayı.
Eksi bir sayı diyeceğim, eksi bir pozitif sayı.
Yok, yani geografi pozitif sayı.
Doğru aslında.
Eksi negatif de olur.
Eksi bir pozitif kalsın. Doğru doğru. Ama eksi bir pozitif sayı enteresan bir şey. Tamam mı? Bu borderline stable. Hangisi borderline stable? Hangi point tamam?
Zero yok aslında.
Does it make, well, do you agree with it? What does it say? It basically says,
Burada durmaz mı?
if you have this vacuum, you know, with no resistance, no friction, nothing, if you start on zero, you stay there, that's technique. If you don't start on zero, it will neither go away from zero, nor approach zero, stay in the same fixed envelope in zero, which says basically, more technically, it says it will do constant amplitude oscillations, which is correct. So in this case, the result is correct. You know, this linear result. You remember I said here, borderline stable is not always correct. Do you remember this? Yes. Now you know it's correct from your physical experience. Physically, you know it's correct. You know that physically it will make a constant amplitude oscillation forever. So that's a physically correct result in this case. The linearization works. Alright, so what's the other one? What's the other case? Huh? What's the other case? 2 around 5. But in that case, you get something like this. It's approximately equal to. This time, let's see if you agree with this. This is what you get. But it's the same story, same thing. The functions are all the same, except that what you have here. Pi minus theta and g cosine theta. So the only thing that changes is the what? This number. Okay? Okay? So, and cosine theta is what? This time it's minus 1, right? So then you get, if this is minus 1, then what do you get? Theta minus pi times g. Is this correct? And if I call this z again, I get basically something like this. And I put L on the side, d squared, z over dt squared equals some g over L times z. Is this correct? And what do you conclude from here? This is a positive number here, so you basically get what? One of the roots is positive, right? So you get square root of this, some positive number. So one of the roots is positive, so a positive root. Therefore, unstable. So when this says what? No matter how near you start you move away from the equilibrium. Okay? You don't approach asymptotically, nor do you stay in the one. In a close neighborhood, whatever. You move away from it, you go to another equilibrium point actually. You go to this. So that's also a physics correct to know. Alright. Now, with this discussion, this completes our, basically, as I said, there are some other methods. There is something called perturbation analysis, which is very similar to this. If you read it, when you draw the parallel, if you come across perturbation analysis, you see it's so similar to this, just a slightly different way of looking at it. But the same idea. They are also, perturbation analysis is also based on essentially Taylor series. One thing, here is the next topic. The next topic, we put the title for the next topic. The next topic is phase plane analysis of systems. Okay? Phase plane.
Cumartesi optimum kontrolü sınavımız var.
Ha?
Konu bu.
Vay be. Biraz daha hızlı anlatsam. Ben bir anlatırdım. 45 dakika tamam hani. Çalışmaya güzel. Ha? Ne? Hangi cuma sınavı? Ha öyle mi? Ha, o zaman geçtiniz sınavı. Hiç başka hiç yapmadınız. Ha tamam. Ben cuma deyince şey zannettim ya.
Doğru işte hafta cuma.
Ha o zaman tamam. O zaman hızlanalım biraz. Bakın, o derste bir defa daha duymuştum. Phase plane konuşuluyormuş, phase analiz. Phase plane nedir filan gibi. Başka bir de differential equation'lar filan. Calculus of variations da var. Öyle bir metot filan da var. Ha? Ben size bir şey soracağım. Şimdi adoptive control theory.
Bundan sonra
Şimdi
Calculus of variations anlatmadan anlatamaz. Yani calculus of variations biraz gerekli. Optimum kontrol teori için. Tamam mı? Fakat şeyi anlamıyorum. Bunu biraz inceleyip bana söyleseniz. Hepiniz arıyor musunuz? Bana bunu bir kısa bir rapor verin sonra. Hayır, çok yararlı bir ders olabilir. Derste şöyle bir imaj alıyorum ben. Bambaşka bir konuya gidip. Bu biraz fakulty toplantısında konuşuldu bu konu. Şimdi kendine vererek yapıyor. Gayet hoş bir şey yani. Dışarıdan bir adam, sanayi bir adam. Böyle bir de şey bir konu, hani öyle ticari bir konu değil. Gayet bilimsel bir konu anlatmak için uğraşıyor. Ve şey diyor, daha iyi anlatmak istiyorum, sığamıyorum diyor. Bana 2 ders açmama şey yapın. 2 ders verin bana diyor şimdi. Fakat tuhafıma giden şu, ben biraz incelediğim zaman 2 ders versin de bambaşka bir ders daha verse daha faydalı olur. Yani bu dersi hakikaten optimal kontrol teori bound'u içinde verse bu ders sığar. Yani bu dersi de siz bana anlatın sonra. Nasıl anlatıyor ki? Söyleyin. Optimal kontrolda hakikaten mesela Euler metodu ve phase plane'i kullanacak diyelim. Ha, amacı optimal kontrol dersin abi. Yani sonunda her şeyin optimal kontrol etkiyle etmesi lazım. Değil mi? Dersin adı optimal, dersin adı şu. Bir dinamik sistemin optimal kontrol algoritmaları ne olabilir? Doğru mu? Dersin amacı bu. Öyle anlatılmıyor derste. Dinamik sistemlere bir giriş yapması doğal. Bu doğal. Ama arkasından calculus ve variations background anlatılması da doğal. Benim şaşırdığım şey, 2 tane şaşırdığım konu var. Euler metodu, yani Euler metodu bir numerical solution değil.
Çok uzun hafta.
Onu merak ediyorum. Ha? Ne?
4 haftalıklar mı sürüyor?
Ne?
Öyle. Ya mesela özel halleri gitmekler de var.
Ha?
Çok yavaş
Ha. Sen iyi orada dinle. Şimdi bu dikkat ederseniz burada nth order classical nth order nonlinear differential equation formatında şey tartıştık. Stability yani. Tamam mı? Halbuki yine nth order nonlinear systems of equations olabilir. Daha iyi esas kullandığımız, model kullandığımız çok flow modelleri first order set of nonlinear differential equations. Onun epey bir analizini, bütün hani equation'ların analizini face plane denen teknikle bayağı 2 hafta tartışacağız. Ama başında burada bir tane küçücük bir şey kaldı. Ona dikkatini çekelim. Gelir gelmediğini göstereceğim. Başında bir parantez açıp ben face plane'e fazla girmeden şey göstereceğim. Peki bizde single nth order classical differential equation değil de n first order set of nonlinear equations olsaydı yine linearize ederdik değil mi? Tek farkı ne olurdu? Her birini ayrı ayrı şöyle n variable'lı Taylor. Anlatabildim mi? Yani f of x1 x2 f of x1 x2 x3 neyse işte f of her bir f onun ikincisi ne olacak? Her birinin ayrı ayrı fonksiyonları olacak. Her bir fonksiyonu tek tek linearize edecek. Linkler falan yapmanlar. Ondan bir örnek göstereyim ki. Yani sebebi de şu. Linearization'ı kapatalım. Linearization'ı face plane içinde kullanacağız ama linearization olayını bir kapatalım. Ondan sonra face plane'e yani 10 dakikalık falan olacak. Bunu şu anda yapabilirsiniz. Böyle hepsini. Son
Hocam bir şey
galiba son 2 soru hariç. Yok. Son soru hariç. Yani son soruyu konuşmak. Çünkü son soru şey diyor. Nonlinear system of equations. Bir tek onu o hariç hepsini yapabilmeniz lazım bu soruları.
Hocam bir de mesela second order değil de mesela third order.
Bu mu gördün? Tabii. O zaman 3 variables olacaktı. Niye burada d square ve d square olacaktı genel olarak. O zaman bu da 3 variable'lı Taylor expansion olacak. Yani 3 tane teorem olacak. Yani 2 tane.
Hocam bir de burada bu pendulumda bir tane equilibrium point unstable çıktı ya. Sistem globally unstable deriz. Yani genel global sistem için ne söylenir?
İlla seni sıkıştırırlarsa, illa bıçak değer varsa öyle diyebilirsin ama nonlinear sistemin onun için global stability konuşmayı sevmiyorum. Çünkü o her ne dersen de incomplete bir cümle oluyor. Well defined bir cümle olmuyor. Doğru olanı bu sistemin bu equilibrium point stable, diğer equilibrium point unstable. Complete cümle o. Onun için global stability cümlesi kullanmayı pek fazla sevmiyoruz şeyle ilgili. Nonlinear sistemlerle ilgili. Çünkü yani sistem unstable demek çok doğru bir cümle değil, characterization değil. Şey izlenimi veriyorsun. Yani bu sistem hani hiçbir yere settle etmiyor, izlenimi veriyor. Halbuki bir yere settle ediyor. Anlatabiliyor muyum? Dolayısıyla bu nokta unstable ama sistem unstable demek doğru bir şey değil fazla.
Hocam birdeki borderline stability mesela hani ne kadar uzaklaşırsa etrafına dönüştürüyor da aynı şekilde dönüştürüyor şeklinde algılanabilir mi?
Evet.
Yani az olursa az gelecek ama perturbation çok olursa çok yani attribute'u belirliyor işte senin.
Yani bu borderline değil mi? Bu çok özel bir durum. Çok özel bir borderline durumu bu. Spesifik bir durum. Bu şu. O envelope var ya o region of stability. Buradan başlarsan kocaman oluyor. Buradan başlarsan küçücük oluyor. Bu özel bir durum. Bazılarında daha ince problemlerde şuradan başlarsan içinde kalırsın, buraya gidersen başka yere gider. Bu öyle değil. Yani bu çok daha broad ve strong bir şey. Borderline stability. Nerede başlarsan orada kalıyor etrafında. Bazı problem vardır. Şu kadar aralıkta başlarsan oynar, burada başlarsan başka yere gider. Bir şey düşünsene de şöyle bir şey gibi düşünün. Yani şöyle bir şey düşünün. Şöyle bir dağ ve yamaç vadiyi düşünün. Şöyle biraz da şöyle düz yap yukarıyı, şöyle düz, ötesi düz. Şöyle bir şey. Oralarda başlarsan kalırsın ama burada başlarsan öbür tarafa düşersin. Ama düzgün bir şey, şöyle bir şey. Buralara koyarsan topu durur.
Biraz daha aşağıdan bırakırsan kalır, biraz daha yukarıda bakırsan uçar gider.
Biraz daha bırakırsan? Hayır. Hayır bak, sana güzel bir şey göstereyim. Ne diyorsun değil mi? Buraya koyarsan durur, buraya koyarsan durur, buraya koyarsan durur, buraya koyarsan kaçar. Bunun modelini kurabilirsin, gayet güzel. Sen de ne bahsediyorsun?
Ben şuranın olmasından bahsediyorum. şöyle mesela.
Ha?
Bu şekilde.
Ha, bu da böyle.
Şuradan bırakırsak kalıyor.
Ha, tabii,
Şuradan
tabii.
bırakırsak
Ha, o ihtimal
böyle
yok.
gidiyor.
Tabii ben şimdi böyle çizdim, daha da enteresanı var. Burada bırakırsan, bunun modeli buradan çok enteresan. Gayet sofistike bir model şu şey. Burada bırakırsan buraya gidiyor, burada buraya gidiyor, burada bırakırsan gidiyor. Burada bırakırsan burada bırakırsan tekrar buraya çıkabilir. Vardır ya oyun.
Ha, evet.
Bu oyunun